Hello, everyone, and welcome back. In this lecture, we're going to continue our discussion of sequences and present one of the most essential theorems in all of real analysis. That is going to be the Bolzano-Weierstrass theorem. Now, there's something that you can carry with you through all of mathematics, and that is if a theorem is named after the people who first proved it, then it's important, right? And so the Bolzano-Weierstrass theorem is named after two mathematicians, Bernard Bolzano and Karl Weierstrass. And interestingly, they're sort of sharing credit on this theorem, but it turns out that Bolzano proved this much earlier than Weierstrass. But the problem was that Bolzano proved it in 1817, and it was just a little lemma as a stepping stone to proving the intermediate value theorem, which we'll eventually get to in this class, but you might be familiar with if you've taken a calculus class before this. So it actually wasn't until about 50 or so years later that Weierstrass proved this theorem again, and it sort of got a little bit more attention because it wasn't sort of buried in Bolzano's theorem. Now, the Bolzano-Weierstrass theorem is quite simple to state. It says that if you have a bounded sequence, so it doesn't have to converge, just bounded, then there's a subsequence that converges. Now, the problem there is that we haven't discussed subsequences. So that's going to be what we're going to start with. We're going to start with the definition of what a subsequence is and try and work through that a little bit and eventually get ourselves to the statement and the proof of the Bolzano-Weierstrass theorem. So let's go ahead, let's jump right in, and let's do exactly what I said and start with the definition of a subsequence. So much like many of the classes, we're going to start with a definition here. So we have the definition. Okay, we're going to say let n sub k be any strictly increasing. Now, you've seen strictly increasing before. This means strictly greater than, no greater than or equal. So strictly increasing sequence of natural numbers. Okay, so this is a little different so far because typically we've been looking at strictly increasing sequences of real numbers. So that's where the little n comes from here to denote that this is a natural number. And this really means, again, just the definition of strictly increasing. N1 is less than N2, which is less than N3, which is less than N4, and so on and so forth. Then we call x sub nk, so an element of a sequence sampled at only the n1, n2, n3, the n sub k terms. We call this thing a subsequence of a sequence xn. Okay, so what this means is that you're sort of collecting an infinite sample of a sequence. So you don't have to take every single element, but you sort of scan through the element and you sort of pick them out like apples. You say, I want this one, and then I've got to pick another one further to the right. That's what that strictly increasing piece says. Then you say, I want this one, and we continue on with that. So let me draw a little picture. Here's x1, here's x2, here's x3, x4, x5. I'm just going to draw a lot of them so I can really illustrate this. So this is x7. Let's go up to x8. This is my sequence. And so my subsequence just selects a subsample of these things. So maybe I don't want x1, but I want to take x2. And I don't want x3, I don't want x4, I want to take x5. I want to take maybe x6. I'm sort of choosing here randomly. Maybe I'll choose x8. And I continue going on with this ad infinitum. So the point is that when you choose an element from the sequence, you can only choose the next element further to the right. So beyond this. All right, so my subsequence is x2, x5, x6, x8, and so on and so forth. Now, there's another way you can think of this, sort of the calculus method. So let me start with a little remark here, RMK. So first of all, since N1 is a natural number because I define the natural numbers to start from 1. This thing is by definition bigger than or equal to 1. So look at my previous example. Sorry, that's N1. Look at my previous example, N1 was 2. But then, because this thing is monotonically increasing, it follows that N2 is greater than or equal to 2. So in my previous example, that's 5. And you can repeat this process, and you get that Nk is greater than or equal to k. And this is true for all k greater than or equal to 1. Now, another way you can think of this is we can notate, subsequences by n sub k is equal to some function of k, where this phi, this function, is a function from the natural numbers into the natural numbers. So you put in a value of k, a natural number, and it returns to you another one. And this thing has to be a strictly increasing function. Right, so that's sort of how you can think of this thing. Again, if you're thinking of sequences as being functions from the natural numbers into R, then now you're thinking of a composition. So you're finding this phi function, which subsamples your natural numbers. And then once it subsamples them, then you use that to identify elements of your sequence. So it's a two-step process, which is exactly a composition of functions now. Now that might be a little more abstract than you care about, and that is perfectly fine. Let's take a look at some examples. So let's let xn equal to, say, n squared, right? So you give it a natural number and it returns to you the square of said number. And this is for all n greater than or equal to 1. Well, one possibility is if we say nk is equal to 2k. So this is the even natural numbers, right? Because anything multiplied by 2 is even. And since k goes from 1 all the way up, you're selecting every natural number, every even number, 2, 4, 6, 8, 10, and so on. And so this means that xnk is equal to 2k squared, which if you wanted to, you could write as 4k squared, which is a sequence of squares of even natural numbers. Right, so you feed into it 2, 4, 6, 8, and what you get returned are 4, 16, 36, 64, and so on and so forth, right? We're sort of stretching my arithmetic while I'm trying to do this, but that's the general idea. And so that would mean that my phi function, so maybe if I just make a little note, phi of k is equal to 2k. It's a linear function. And you can do this in any way that you want, right? You could maybe select the odd numbers and come up with a sequence of odd squares. And you can do this maybe if you take every third number, or every fifth number, or every 100th number. But the important piece here is that you do not have to do it in such a way that you're selecting a regular pattern. Again, look at my picture up here of the red sequence in the green subsequence. There seems to be no sort of rhyme or reason. I'm sort of just picking elements randomly, and that's perfectly fine. Now, let's start with a nice little result here. It's a very, very quick and simple one. And it says that if xn converges, so we have a sequence and we know it converges to the limit L as n goes to infinity, then every subsequence, x and k also converges to L as n goes to infinity. So that's interesting, right? It says no matter, if you have a convergence sequence and no matter how you subsample that, then you are going to find yourself with a convergence subsequence. Okay, so this may look like a complicated result, but what's really, really nice is that the proof of this thing is really just sort of following definitions. So let me show you. It's pretty much a one-line proof for what I think is a pretty powerful result. So we're going to prove by definition. So we're going to say let epsilon be bigger than 0. Again, anytime we want to prove a sequence converges, we've got to use that unless we have some algebraic combinations that we can evoke the previous lecture from. Well, then there exists a capital N such that for all n greater than or equal to n, this implies the original sequence is within epsilon of its limit. But since since n sub k is greater than or equal to k for all k, it follows that if we choose k bigger than or equal to capital N, this implies that n sub k is greater than or equal to capital N, which in turn implies that we are looking far enough into the sequence so that the original thing was converging. But thus, this shows that xn sub k converges to L as n goes to infinity. So again, just sort of one line, really the only piece of this that presents anything really useful here is just knowing that n sub k is greater than or equal to k for every value of k. So we have an immediate corollary associated to this, so a direct consequence. And this says that if xn has two subsequences that converge to different limits, right? So you found one subsequence that converges to say L1, limit 1, and another subsequence that converges to limit 2, L2, and L1 and L2 are not equal to each other, then it's impossible for xn to be convergent. And this doesn't require a proof because it's immediate from the previous theorem, right? Because if xn was convergent, then both of the subsequences would go to the same limit. But we assume that they go to different limits. And so we see that we can't have a convergent sequence. So let me give you an example of a sequence where this would be applicable. We can say, let's use one of our favorite sequences that we've defined in this class, that one that alternates between -1s and 1s over and over and over again. So note xn is not, xn is bounded, of course, right? We've already seen this before, but we proved previously xn is not convergent, right? We did that in the second lecture using Cauchy, showing that it's not a Cauchy sequence, but we can actually do this in an easier way, right? We could say the subsequences, so you can, subsequences, if we take all of the even terms here, well, then this is just equal to -1, which implies that x2k converges to -1 as k goes to infinity. So one subsequence converges to -1 because it's just a constant sequence of -1s. But alternatively, if you look at all of the odd terms here, sorry, this should be 2k -1 since k starts at 1. This gives you +1, which tells you that the odd subsequence converges to +1. And so now you've identified two subsequences that have different limits. So from the previous corollary, xn does not converge. And again, that just comes from the fact that we identified two subsequences that both that converge to different limits. But there's something that I threw out there that you probably felt like wasn't really that important. And I pointed out that xn is bounded. Now, if you were paying attention at the beginning of this video, you know why I pointed out that xn is bounded, because this is an important component of the Bolzano-Weierstrass theorem. So let's, now that we have all of the language and the techniques built up, let's actually present the Bolzano-Weierstrass theorem. And once we present it, I want you to take some time to go back to this example and see exactly why I pointed out that it was bounded and how the Bolzano-Weierstrass theorem might apply here. Okay, so let's say let xn be any bounded sequence of real numbers. So that there exists an m in R such that xn is less than or equal to m for all n greater than or equal to 1. All right, so m is a positive number, of course, by definition here, for this to be true, but I just said that it's a real number, just whatever. Okay, so then there exists a convergent subsequence. xnk of xn, and that means, so that is, there exists a subsequence. So we're putting a lot of qualifiers on this so you can really understand what it's saying. xnk, that converges to some L in minus m to m. So again, like I said, this is what's called the Bolzano-Weierstrass theorem. So it's a very, very, very famous theorem in not just analysis, but all of mathematics. Now, I just want to address, before we get into the proof, some of the shortcomings of this, right? So first of all, it doesn't tell you how to identify the subsequence. Now you'll see with the proof, it's sort of semi-constructive, but again, it still doesn't say exactly what the subsequence would be. It just tells you that one exists. Furthermore, it doesn't tell you what it converges to. It just says there exists a limit. So these are some of the shortcomings, right? There's a very, very theoretical statement. It just says that if you have a bounded sequence, there exists, I'm not sure what it is, but there certainly exists a convergent subsequence. Now, the other thing is it doesn't tell you how many convergent subsequences there are. Again, look at the previous example. That thing is a bounded sequence, and I found 2 different convergent subsequences. So, you know, of course, Bolzano-Weierstrass applies in this case, but it doesn't tell you everything about the sequence, right? So you have to be conscious of what some of the shortcomings are here, but also what the strengths of this theorem actually are. And let's take a look at the proof. The cool thing is this is going to use that interval halving technique that we saw a few lectures ago, where we proved the existence of a least upper bound. So let's define a sequence. A1 is equal to -1 and B1 is equal, or sorry, minus M, and B1 is equal to M. So this tells us that every element of the sequence is in A1 and B1 for all n greater than or equal to 1. Right? So that comes from the fact that we assume that this thing is bounded. So there's an interval that it lies in. In our case, it's -m to m, because we have that absolute value of xn is less than or equal to m. So we're going to construct, so sort of quote unquote construct, it's going to be abstract still, but we'll construct the subsequence. We're going to say let the first element of the subsequence be the first element of your sequence. Okay. Now we will divide this big interval in half using the midpoint. So same thing that we did with that least upper bound proof. Again, the midpoint is A1 plus B1 over 2, which is in our case equal to 0 because it's a symmetric interval, right? -m to m. Okay, so now we have two cases. So if there exists infinitely many values of n such that xn is between a1 and the midpoint of the interval, so it's in the left half of this interval, then we will let a2 equal to a1 and b2 equal to the midpoint 0. Similarly, so in the alternative case, if there does not exist infinitely many values of n such that xn is between a1 and 0, then there must be, so then there exists infinitely many terms or elements, or however you want to say this. Let's say infinitely many elements of xn in the other half of the interval. And I'll explain this in a second. So in that case, let a2 equal to 0 and b2 equal to b1. Okay, so how does this work? Okay, so we have infinitely many elements of our sequence xn that lie between minus m and m. We cut the interval in half and we say if there's infinitely many on the left, then let that be our new interval. But if there's only finitely many in there, then by the pigeonhole principle, I have infinitely many on the right half of this interval, right? So again, think about you and your neighbor have mailboxes and infinitely many letters came between the two of you. Well, then somebody got an infinite number of letters, right? Both of you couldn't have just gotten finite letters. That's the principle that's at work here. So you're sort of chasing down the half of the interval that has infinitely many terms in it. Okay, so this says now, since there exists infinitely many terms of xn in the new interval a2, b2, which is half of the previous interval, we are going to pick any n2, which is bigger than n1, such that xn2 belongs to a2, b2, right? So there's infinitely many in there. I don't care which one you pick, just pick it. Okay, now we're going to repeat that process. So next, divide a2, b2 in half, equal halves, and pick one of the halves. Let's call it a3, b3, of course, same idea, interval halving over again, over and over again, having infinitely many terms of xn in it. So again, the whole interval contains infinitely many. So when you divide it in half, one of those halves has to have infinitely many again. So then let's pick an n3 that's bigger than n2. Again, we can keep going because we're unbounded in one direction here, such that xn3 is in this now smaller interval, right? So this is a quarter of the original interval. And I'm just going to say repeat. So at every single time, find an interval, cut it in half, pick the half with infinitely many terms. You can keep doing this over and over and over again, and you get a subsequence. So we get, first of all, we should observe, since at every point we are having the intervals, then your interval bk, or ak to bk, the length of that thing is going to be the length of the original interval, 2m, divided by 2k minus 1. And that's just the number of halves that you've taken to get down. And of course, this thing goes to 0 as k goes to infinity. So that tells you that the width of your interval is going all the way to 0 very, very quickly. So if epsilon is bigger than 0, there exists some capital K in n such that if you look at k beyond capital K, this implies that, b sub k minus a sub k is less than epsilon, right? That just comes from the fact that you are having the intervals and eventually, the intervals are getting very, very small. And so eventually everything is going to be smaller in width than epsilon. Okay, let me go to the next page here, because what does this mean for our subsequence? Well, this means that thus, if j and k are both bigger than or equal to capital K, we have xnj minus xnk. So these are elements of my subsequence. I've been chasing around down all of these little splittings of the interval. Well, these things are also less than epsilon. And that comes to the fact that they belong to the interval b sub k minus a sub k, right? And this is the same thing that we saw with the least upper bounds, right? These things are sort of nested. At every single step, I'm just taking the previous one and going half. So that means if I look beyond capital K, everything is in the capital K interval, which was smaller than epsilon. So this is as well. But this tells me that I have a Cauchy sequence. So hence, xnk is a Cauchy sequence. I'll put like sub in brackets here. It's a subsequence, but it is itself a sequence. And so must converge to a limit in R, right? This is just the completeness axiom coming in again. So remember, right, we're sort of using everything that we've built up so far, and it's all sort of culminating and avalanching forward. Furthermore, since minus m to m is a closed interval, we know from our previous work with the least upper bound, or maybe we can show, as in the previous work with the least upper bound, that the limit of x and k is in minus m to m. So I'm going to leave that piece of the proof sort of hanging there for you. But this is actually a pretty straightforward thing to do. If you want to prove it wrong, you say, imagine the limit is outside of that. Then you just say, set epsilon equal to the distance of your limit to the interval. That thing is positive because you're outside of the closed interval. And then you can arrive at a contradiction, just like how we did with the least upper bound. So I'm going to leave that piece as a titillating little aspect of this that I want you to sort of work out on your own. But the point here is that now we have seen exactly two proofs that use the interval halving method. And we can see that the real benefit of using interval halving is that it produces a Cauchy sequence. And we know that when we have Cauchy sequences in the real numbers, the completeness axiom tells us there's a limit. So this is a really, really nice way to show that we have sequences that converge just by doing this sort of halving and sort of breaking things up and crushing them down into these tiny, tiny, tiny little intervals that we can sort of chase infinitely down the rabbit hole.